Hello everyone, welcome back to Sulekha physics classes. It is the most easiest way to learn all the concept of physics through this class. Today I am going to start one short revision of chapter 6, Electromagnetic Induction. In this chapter we will discuss many important topics like Faraday's experiment, Faraday's law, Lenz's law, self-induction, mutual induction, and all these topics are very important. Okay, so in the previous chapter we discussed about magnetic effects of electric current, right? Magnetic effects of electric current means how magnetic field is produced with the help of current, right? Here in this chapter, electromagnetic induction, we will discuss reverse thing of this one. How current is produced with the help of magnetic field. This is called electromagnetic induction. So electromagnetic induction is the phenomenon of production of what? Current, na? Induced current and induced EMF due to what? Due to this change in magnetic field, na? And due to this change in magnetic field lines are changed, and that is called magnetic flux. So due to change of magnetic flux linked with the closed circuit. I will discuss what is magnetic flux. So this phenomenon is called electromagnetic induction. It is the phenomenon of production of induced EMF and hence induced current due to what? Due to change in magnetic flux linked with that circuit, right? So first in this definition one term is there. What do you mean by this magnetic flux? Magnetic flux is represented by phi b, like electric flux is also phi, na? Phi E is electric flux and phi b symbol represents magnetic flux. It is total number of magnetic field lines crossing through any surface normally when it is placed in a magnetic field. Suppose this is the direction of magnetic field, right? Magnetic field lines are going like this one, and you place one surface normal to this magnetic field. Suppose this is a surface, right? This one is surface, and this surface is placed normally with the field lines, right? So this is the area of the surface, and you know area vector. Area vector is always perpendicular to the surface, right? So magnetic field is also in this direction, passing through this surface normally, and area vector is also in this direction. If you rotate this plane, then area vector also changes. Now perpendicular this surface is this one, but magnetic field lines are in this direction, area vector is in this direction, it makes some angle theta. So angle between magnetic field and area vector is theta. You must remember that area vector is always normal to the area, right? And if magnetic field and area vector both are in the same direction, it means maximum lines pass. If both makes angle 90 degree, it means magnetic field lines going like this one and this plane becomes this one. So it just passes, magnetic field lines just passes through the surface, does not pass through this area, right? And in that case magnetic flux is 0, right? So magnetic flux is nothing but dot product of magnetic field and area vector V dot A, and it is equal to BA cos theta. Theta is the angle between this magnetic field and area vector. It is a scalar quantity. Why it is a scalar quantity? Because it is dot product of two vectors, so it is a scalar quantity. Its SI unit is Weber. Weber is represented by you can write W, capital W, small b, or also SI unit of this magnetic field is Tesla and area is meter square. So Weber is also equal to Tesla meter square. And in CGS system, its unit is Maxwell, represented by M, capital M, small s, or Gauss centimeter square. What is the relation between this Weber and Maxwell, right? 1 Weber is equal to Tesla meter square. Tesla is what? 10 to the power 4 Gauss. Meter, 1 meter, 100 centimeter, it means 1 meter square, 10 to the power 4 centimeter square. So it is equal to 10 to the power 8 Gauss centimeter square. You can say 1 Weber equal to 10 to the power 8 Maxwell. This is the relation between SI unit and CGS system. 1 Weber equal to 10 to the power 8 Maxwell, right? Its dimensional formula is ml square T minus 2, A minus 1. So I think this is clear. What do you mean by this magnetic flux? Magnetic flux is total number of field lines passing through this surface normally when it is kept in a magnetic field. And when angle is 0, it means both area vector and magnetic field lines are in the same direction, then maximum flux. Maximum lines passes through the surface. But if both are at 90 degree, suppose magnetic field is in this direction and area vector is in this direction. So this one is magnetic field, this one is area vector, both makes angle 90 degree. In that case, flux is minimum. So why we discuss this magnetic flux? Because when we discuss about electromagnetic induction, Faraday's law, in that one magnetic flux term is used. So you must know what do you mean by magnetic flux. It must be clear. Also, if number of lines passing through a small surface area, suppose this is small area dA, in that case magnetic field lines passing through this small area element is d phi equal to B dot dA. So how you calculate total magnetic flux through this whole surface area? In that case, you just integrate this small magnetic flux over the whole surface area, B dot dA. Right? This is the magnetic flux for total surface area. If you know small magnetic flux through the small surface area element, you can easily calculate total magnetic flux. You can just integrate over the whole surface area. In this way, you have to use magnetic flux formula, right? Please take a screenshot of this one. Then we'll move to the next topic. Now, Faraday's experiment. Faraday and Henry performed various experiments and both came to the conclusion that whenever there is change in magnetic flux linked with the closed circuit, EMF is induced and hence current is induced in that circuit. Or whenever there is relative motion between the two coils or coil or magnet, EMF is induced and current is produced in that circuit. So how you perform the experiment? There are three experiments. Experiment number 1, in first experiment, there is a stationary coil and moving magnet. Coil is stationary and a galvanometer is connected to a coil and magnet is moving. First magnet is moving towards the coil, next magnet is moving away from the coil, and third I have taken magnet is at rest. When the magnet is moving towards the coil, this galvanometer shows deflection in this direction. Right? When a magnet is moving away from the coil, again galvanometer shows deflection in opposite direction. And when the magnet is at rest, then the galvanometer shows no deflection. Why? And also if the motion is rapid, then again deflection is more. More deflection means current is flowing in that circuit. Right now? Why it shows deflection? When the magnet is moving towards the coil, then magnetic field lines passes through this coil. Right now, number of field lines passing through this coil. When it moves closer to the coil, more number of field lines passing through the coils. It means number of field lines changes, it increases. There is a change in number of field lines. It means magnetic flux is changing, and hence here if magnetic flux is changing, this galvanometer shows deflection. Again in this one, when magnet is moving away from the coil, then field lines passing through this coil decreases, right? If it is moving away from this coil, then field lines passing through this coil decreases, either increases or decreases. There is a change in magnetic flux, and hence this galvanometer shows deflection. If there is no motion, then there is no change in field lines. If 4 field lines are passing, then every time only 4 field lines are passing. No change in field lines, it means no change in flux. Change in flux is 0, hence galvanometer does not show any deflection. From here it's clear that whenever there is a change in magnetic flux linked with this coil, then this galvanometer shows deflection. It means some current is flowing through this coil, right? Again, this is experiment 1. In experiment number 2, here magnet is stationary but coil is moving. Now this time one galvanometer is connected to this coil. When this coil is moving towards this magnet, what happens? Again, number of field lines passing through this coil changes. If it is moving towards the magnet, field lines increases. If it is moving away from the magnet, field lines decreases. Again, there is a change in magnetic flux. And if there is change in magnetic flux, this galvanometer shows deflection. It means current is induced in this coil, right? This is second experiment. Now in third experiment, he has taken two coils, one C1 and the one is C2. In C1 coil, galvanometer is connected, and in C2 coil, one battery is connected, right? Battery is connected, it means this is positive terminal, current is flowing in this direction, this one, right? In this direction, current is flowing. Now if this C2 coil, in the coil in which the current is flowing, it moves towards the coil. Now what happens? You know, a current carrying coil produces magnetic field around it now, right? So magnetic field is produced around this coil if constant current flows. But if this coil is moving towards this another coil, neighboring coil C1, then that magnetic field lines passing through this coil, right? And if it comes closer to this coil, again field lines is changing, right? And due to this change in field lines, flux is changing, and if flux changes, this galvanometer shows in the neighboring coil, C1 coil, galvanometer shows deflection. It means some current is induced in this coil. So from all these experiments, and if motion is rapid means galvanometer also shows more deflection. More deflection means more currents. So from all these experiments, he came to the conclusion that whenever there is change in magnetic flux linked with the coil, an EMF is induced in the coil, and hence if the coil is closed, current is induced in the coil. So this is all about Faraday's experiment. On the basis of these experiments, there are two laws of Faraday, Faraday's first law and Faraday's second law. So first take a screenshot of this one, then we will discuss that one. Next, on the basis of Faraday's experiment, there are two laws of Faraday. Faraday's first law and Faraday's second law. In Faraday's first law, it states that whenever a magnetic flux linked with the coil changes, whenever there is change in magnetic flux linked with that coil, an EMF is induced in the coil. And if the coil is closed one, then induced current flows through the coil. This is Faraday's first law, that whenever there is change in magnetic flux linked with that coil, then induced EMF or induced current is produced in that coil. Now, what is the magnitude of that induced EMF? It was given in Faraday's second law. According to Faraday's second law, actually it is mathematical form of Faraday's first law. It gives magnitude of induced EMF, and the magnitude of induced EMF is equal to rate of change of magnetic flux linked with the coil. To which rate magnetic flux is changing? According to that one, EMF is induced in the coil. So this magnitude of induced EMF is equal to d phi by dt, rate of change of magnetic flux. So, but it gives only magnitude, d phi by dt. What is direction of induced EMF? What is direction of induced current, right? It was given by Lenz's law. The direction of induced EMF for induced current is given by Lenz's law. E is equal to minus d phi by dt. This negative sign gives direction of induced EMF. And what is direction of induced EMF? It is always opposite to the rate of change of magnetic flux. It means, according to Lenz's law, the direction of induced EMF or current is such that it opposes the cause which produces it. Who produces induced EMF or induced current in the circuit? Change of magnetic flux. So the direction of induced EMF is such that it opposes the change of magnetic flux. It opposes the cause which produces it. It opposes the cause which produces it. And who produces? Change in magnetic flux. If induced EMF is produced in the circuit due to increase in magnetic flux, then direction of induced EMF of current is such that it tries to decrease the change in magnetic flux. If it is produced due to decrease in magnetic flux, then direction of induced EMF is such that it tries to increases the change in magnetic flux. So let it be more clear with the help of some examples. First you note down, take a screenshot fast. Now, how you determine direction of induced EMF or current according to Lenz's law? Okay, so here are some examples to determine direction of induced current or EMF according to Lenz's law. In the first example, let us suppose that field is inward. Inward field is represented by cross time, and this field is not constant. It is changing with time. And suppose you place one coil inside this magnetic field. Now, what happens? Due to change in magnetic flux, here suppose magnetic field is increasing. Due to increase in magnetic field, magnetic flux also increases inside the coil, and due to change in magnetic flux, what happens? EMF or current is induced in the coil. What is the direction of that induced current or EMF? So according to Lenz's law, direction of induced current is such that it opposes the cause which produces it. Now here, who produces induced current? Increase in magnetic flux, due to increase in magnetic flux. So direction is such that it tries to decreases the magnetic flux. Now direction of induced current is such that it tries to decreases the change in magnetic flux, and magnetic flux is decreasing only if you take the reverse direction of magnetic field. Here magnetic field is inward. If you take magnetic field outward, then magnetic field flux decreasing. And if magnetic field is outward, right? If magnetic field is outward, then the direction of induced current is what? Anti-clockwise, right? So direction of induced current here is in anti-clockwise direction, right? Why it is anti-clockwise? But because it is produced due to increase in magnetic flux, but direction is such that it tries to decreases the change in magnetic flux, and it is possible only if magnetic field is outward. So direction is anti-clockwise, right? Okay. Now in second case, suppose this magnet is moving towards this coil, and due to the motion of this magnet, when the magnet is moving closer to the coil, magnetic field is again increasing, and there is increase in magnetic flux, right? But the and hence current is induced in the circuit, but the direction of current is such that it tries to decreases the change in magnetic flux, right? And how magnetic flux decreases? If magnetic field is decreasing now, and magnetic field decreases only if the magnet moves away from the coil, and it is possible only if this side is north and this side is south. So direction of induced current is what? North pole. North pole means anti-clockwise direction. So direction of induced current is in anti-clockwise direction. Now in the second case, if the magnet is moving away from the coil, again there is a change in magnetic flux. But here in this case, magnetic flux is decreasing. So direction of induced current is such that it tries to increases the magnetic flux, and magnetic flux is increasing only if this magnet moves towards the coil, and it moves towards the coil only if this side is north, right now? And north means direction of current is what? North, south pole. South pole means direction of current is clockwise, right? I think it's clear. Okay, again. Next, number 4. Okay, here south pole is this side, and magnet is moving towards the coil, right? Again, here current is induced in the coil. In this case also, flux is increasing. So direction is such that it tries to decreases the flux, and flux decreases only if the magnet moves away from the coil. It is possible only if this side is south pole, and south pole means clockwise current, right? Okay. Now in the last one, if the magnet is moving away from the coil and this side is south, so away from the coil means there is decrease in magnetic flux. So direction of current is such that it tries to increases the magnetic flux, and magnetic flux only increases if this side is north pole, so that magnet is moving towards the coil, and due to north pole, direction of induced current is what? anti-clockwise. I think it's clear to you how you determine direction of induced EMF for current according to Lenz's law. It is always in such a direction that it opposes the cause which produces it. Okay, and if it does not, if direction is not given according to the Lenz's law, then it does not holds law of conservation of energy. How? We'll discuss next why Lenz's law is necessary to hold law of conservation of energy. If Lenz's law is not valid, then it violates the law of conservation of energy. Okay, first please take a screenshot of this one fast. Now, Lenz's law and conservation of energy. How Lenz's law is in accordance with law of conservation of energy? What happens if Lenz's law is not valid? Whether it is in accordance with law of conservation of energy or not. Let it be more clear with the help of these examples. Okay. Here, suppose first and second, and in these two cases, Lenz's law valid, right? Lenz's law valid. Now, according to Lenz's law, if the magnet is moving towards the coil, then its magnetic flux increases. The direction of induced current is such that it tries to what? Decreases the magnetic flux. It means this pole becomes what? North pole. So that it repels the magnet and magnetic flux decreases. North pole means the face of the coil towards the north pole of the magnet must be north pole. It means direction is what? Anti-clockwise. Here again, magnet is moving away from the coil. It means there is decrease in magnetic flux. So direction is such that it tries to increases the magnetic flux, and it increases only when the magnet is moving towards the coil. So it must be south pole. The face towards the magnet must be south pole. South pole means clockwise current. These directions are given according to Lenz's law. Now here we are moving the magnet towards the coil against this force of repulsion. Right now, here again we are moving the magnet away from the coil against this force of attraction. It means we are applying some work, and that work appears as electrical energy in this circuit in the form of induced current. So this is in accordance with law of conservation of energy, work done against the force of repulsion or attraction, whatever is it, that it appears as electrical energy in the form of induced current. Now what happens if Lenz's law is not valid? Okay, suppose this is the coil and magnet is moving towards the coil. So this end becomes north pole according to Lenz's law. If Lenz's law not valid, then this end becomes south pole. South pole means the current starts flowing in clockwise direction. Okay, so here the magnet moves with greater speed towards the coil, and hence its kinetic energy increases without expending an equivalent amount of energy, which violates law of conservation of energy. Here we are not doing any external work to move the magnet towards the coil. Its kinetic energy increases without expending any equivalent amount of energy. So it does not follow, it is not in accordance with law of conservation of energy. Right now, so it's clear that magnet gains speed and hence kinetic energy without expending equivalent amount of energy, which violates law of conservation of energy. Thus, Lenz's law is always valid and is in consequence with the law of conservation of energy. So we always put the direction of induced current or induced EMF in according to the Lenz's law, so that it is in accordance with law of conservation of energy. Right now, hope it's clear to all of you. Please take a screenshot of this one fast, then we move to the next topic. Now, next important topic is motional EMF. What is this motional EMF? The EMF induced across the ends of the conductor due to its motion in a uniform magnetic field. If magnetic field is uniform and if you move any conductor across this uniform magnetic field normally, then EMF is induced across the ends of the conductor due to its motion. That's why the induced EMF is called motional EMF, right? So definition of this one is the induced EMF across the ends of a conductor due to its motion in a uniform magnetic field. Suppose this is a uniform magnetic field and it is cross type. Cross type means direction of magnetic field is perpendicular to this plane, right? And suppose a U-shaped conducting rays. This is a U-shaped conducting rays is placed normally to this magnetic field. Magnetic field is suppose this side perpendicular to this plane, and this is a U-shaped conducting rays, right? Now you put one conductor PQ which is able to slide over this conducting rays, right? This PQ conductor is movable over this conducting rays. Now what happens? Due to its motion, original area of this PQRS is something, na? But due to its motion towards left or either towards right, the area of this loop changes, na? Right? If it moves towards left, then area decreases. If it moves towards right, its area increases. And due to change in area, what happened? Magnetic flux changes, and due to change in magnetic flux, EMF is induced across the ends of this conductor, right? So what is the value of that induced EMF? That induced EMF is called motional EMF. So first, magnetic flux linked with the loop PQRS. This PQRS, what is the magnetic flux linked with this loop? B dot A. A is the area of this loop, right? And this is equal to BA cos theta. Theta is the angle between magnetic field and area vector. Suppose this is the direction, inward direction of magnetic field, and this PQ is moving towards left like this one. So it is moving perpendicular normally to this direction of magnetic field. Na? So area vector of this conductor is in this direction, in the direction of magnetic field, right? So angle between this B and A is what? 0 degree. So cos 0 is what? 1. So this flux becomes B into A, where A is the area of the loop PQRS. What is the area of this loop? Suppose this is a conductor of length L. Na? So PQ is L and this is suppose RQ is X. So area of this loop is L into X. So you put the value area here, phi equal to BLX. This is the magnetic flux linked with this loop PQRS. Now this movable conductor PQ is moving towards left, and due to its motion, area changes and EMF is induced. Now according to Faraday's law, what is the value of induced EMF? Minus d phi by dt. You put the value of phi from this equation, BLX. Now here B is uniform, constant. Length of this PQ conductor is also constant. Only this breadth is changing. If it moves through a distance, suppose dx, and then it comes to this position, P dash Q dash, so that the area of this loop changes. So it moves in a time, small time dt, it covers distance dx. So dx by dt is what? V. And why I have taken here negative sign, minus dx here, BL is constant, and minus dx by dt. Motion of the conductor is towards left side, negative x-axis. So minus dx by dt is what? V, velocity, right? So this EMF becomes BLV, or you can write induced EMF equal to BVL. This induced EMF is called motional EMF. And due to this induced EMF, induced current flows across this conductor PQ. Now, what is direction of that induced current, that induced EMF? It is given by Fleming's right hand rule, and also direction is given by Lenz's law also. Suppose here motion of the conductor is this side, right? Now this is the motion of the conductor, and magnetic field is what? Inward. So just motion of the conductor is this side, magnetic field is inward, then thumb is in direction, which direction? Downward. It means the direction in which the thumb represents gives positive terminal of the battery, right? Now so this side positive end and this side negative end, and direction of current flows from this P to Q. This direction is also given by Fleming's right hand rule. According to this Fleming's right hand rule, what happens? You just stretch your forefinger, middle finger and thumb of this right hand right now. Now, okay, it is clear from here. This thumb represents direction of motion of conductor. This forefinger represents magnetic field direction, and this middle finger represents direction of induced EMF of current. Right? Here, magnetic field is inward. Right now, it means you put your this forefinger inward, right? And motion is what? Left side. It means you put your thumb left side. Okay, so magnetic field is inward, you put your thumb left side, then this middle finger represents direction of positive terminal of the battery, right? And it is again downward. Right now, magnetic field is inward, motion is left side, then this thumb is this middle finger is pointing downward. It means downward side is what? Positive terminal. If the motion of the conductor is towards right side, then again magnetic field is this side right now, and motion of the conductor is towards right side. Then this middle finger points upward. In that case, if motion is towards right, positive terminal is upward and negative terminal is downward. So in this way, you can give direction of induced EMF, and here current or induced EMF is from P to Q. Right? Hope you understood about motional EMF and its direction. Please take a screenshot of this one. Now after that, current induced in the loop. You know, when a conductor is moving normally across this uniform magnetic field, and EMF is induced across the end of the conductor, and due to that induced EMF, current is induced in the conductor, right now. So how much current induced in this loop? Let us suppose that this length movable arm PQ has some resistance R. So let capital R be the resistance of conductor PQ of length L, and other sides of this loop has RQ, SR and SP has negligible resistance. So how much current induced in this loop? Only across this PQ, na? So EMF you know BVL. So induced current I is, according to Ohm's law, V by R means E by R. So BVL by R. This much current is induced in this loop, right? Now force on the movable arm PQ. Due to this induced current, it is placed in a uniform magnetic field. Current is induced across this conductor PQ. So due to that induced current, force acts on that PQ arm. What is the value of that force? The force on the movable arm PQ. Here L is length of the conductor PQ, I is current. So force is what? BIL sin theta. Already studied in chapter 4 right now. Here theta is the angle between B and length of the conductor. Magnetic field is inward and length of the conductor is moving towards this one right now. So angle between length and magnetic field is what? 90 degree, right? So sin 90 is 1. So force becomes BIL. Now you put the value of I from this equation. F equal to B into I is BVL by R into L, D square L square V by R. This is the force acts on this arm PQ due to induced current, right? F equal to B square L square V by R. And what is direction of this force which is produced due to this induced current? According to Lenz's law, motion of the conductor is this side, so force is in this direction, outward direction. The force acts in outward direction opposite to velocity by Lenz's law. So now, by Lenz's law, force is acting due to induced current, force is acting outward direction towards right side. To maintain this moving arm, to move left side with some constant velocity V, you have to apply some external work right now, so that the motion of this arm is maintained against this force in right direction, right? So power delivered by external force. So how much power is delivered by the external force to maintain the motion of the conductor? That power is F into V. Force into velocity. Force is how much? B square L square V by R into V. It means B square L square V square by R. This is the power delivered by external force. It means this is mechanical work, and this work is dissipated as Joule's heating loss, right? How power dissipated? This power dissipated as Joule's heating loss. Power is what? I square R na, and I is what? BVL by R. So if you put the value of I, BVL by R whole square, it becomes B square V square L by R. So this the power delivered by the external force is dissipated as Joule's heating loss, right? So this is in accordance with conservation of energy. How? This mechanical energy is expended to maintain the motion of this movable arm, is first converted into electrical energy, means induced current, and then into thermal energy or heat energy. So this is consistent with the law of conservation of energy. In this way, you can derive this expression for power delivered by external force and how it is delivered, dissipated as Joule's heating loss, right? Please take a screenshot of this one. Now next is relation between induced charge and change in magnetic flux. It is very small topic. What is the relation between induced charge and change in magnetic flux, right? So according to Faraday's law, magnitude of induced EMF is what? Rate of change of magnetic flux del phi by del t. If R is the resistance of the closed loop, then induced current is what? According to Ohm's law, I is E by R and E is del phi by del t. So I is equal to del phi by del t into 1 by R. Now this is induced current. So induced charge developed in a small time delta t is what? Delta Q equal to I delta t. Q equal to I t na. So in a small time delta t, induced charge delta Q is I into delta t. You put the value of I from this equation, delta phi by delta t into delta t by R. Delta t cut, it becomes del phi by R. It means induced charge is equal to del phi by R. Del phi is net charge change in magnetic flux and R is resistance. From this expression, it becomes clear that induced charge is independent on time. It only depends on change in magnetic flux, but it does not depends on how much time this change in magnetic flux takes place. It means it is independent on rate of change of magnetic flux. It only depends on change in magnetic flux and divided by R. If there are n number of turns in the coil, then del Q equal to n delta phi by R. So this is the relation between induced charge and magnetic flux, and it is independent on rate of change of magnetic flux. This induced charge only depends on change in magnetic flux, right? So please take a screenshot of this one. After this, we'll move to the next topic. Now, next topic is eddy current. What is this eddy current? This topic is also important for 2 or 3 marks question. Actually, you know that when a conducting coil is placed in a changing magnetic field, then current is induced in that conducting coils. But if a conducting metal plate is placed in between the changing magnetic field, in that case also EMF is induced in the metal plate and then induced current is set up. But that induced current is in the form of closed ring. It looks like eddies or whirlpools in water. That's why that induced current, closed current, is called circular current. You can say is called eddy current, right? So you can write in this way: when a conducting plate is placed in a changing magnetic field, right, or moved in a magnetic field. If you move the conducting plate in a constant magnetic field, then also magnetic flux changes, and due to change in magnetic flux, EMF is induced in a conducting plate. Then there is a change in magnetic flux linked with it. So induced circular current is set up in the conductor, and that circular current, it looks like eddies or whirlpools in water. That's why it is also called eddy currents. The setup is shown here. What happens? Suppose this side is south pole and this one is north pole, right? And the magnetic field lines, it originates from north to south pole. So magnetic field lines are like this one. It is perpendicular to this plane, right? Like this one. And when a solid conducting plate is placed in between these magnetic fields, normally, right now, this is direction of magnetic field from north to south. Inward magnetic field is shown by cross type. So magnetic field lines are along from this north to south, and if you plate a metal plate in between these magnetic field lines, then what happens? Magnetic flux linked with this plate changes, and due to change in magnetic flux, you know, according to Faraday's law, E equal to minus d phi by dt. There is change in magnetic flux, then EMF is induced in this copper plate, right? And the induced current is set up in the form of circular ring, right? These circular currents is called eddy current. Direction of this eddy current is given by Lenz's law, or you can Fleming right hand rule. We already discussed Lenz's law and Fleming's right hand rule before this one, right now. So these eddy currents causes undesirable effect and causes wastage of power. Due to the production of eddy currents, these are just, it produces heating effect, and also wastage of power is there due to the production of eddy current. So we have to minimize that eddy current in conducting plates. So how you minimize? It can be minimized by using laminated core instead of a single solid metal. Instead of a single metal, you have to use cut in between these cuts are there. This is called laminated core is used instead of single solid metal. In this way, you can reduce or minimize eddy current. But if you are not able to minimize all the eddy currents, then you have to use that eddy currents. So there are different applications of eddy current where eddy current can be used. First one is electromagnetic damping. To produce damped oscillation, right? Electromagnetic damping eddy current is used. Also, it is used in electric brakes. Then it is used in induction furnace. In induction furnace, what happens? The metals to be heated is placed in between the changing magnetic field, and due to high heat, this temperature of the metal plate increases and it starts melting. And then also it is used in electric power meters. These are different applications of eddy current where you can use, right? So you must revise what is eddy current. This is important into a 3 marks question. Just revise, learn these definitions, and must draw a diagram also, and direction is given by Fleming's right hand rule. And how it is minimized? It is minimized with laminated core, and there 4 applications you have to learn, right? Okay, please take a screenshot of this one. Next is self-induction. After this, mutual induction. What is this self-induction? Now, what happens when current flows through a coil? Magnetic field is produced around the coil, and if current is changing on variable, then the magnetic field around the coil also changes, and due to change in magnetic field, magnetic flux linked with that coil also changes. Suppose this is a coil right now, and current is flowing through this coil. Now, if current is variable or changing, then magnetic flux linked with the coil also changes. Magnetic flux also changes, and due to change in magnetic flux, what happened? EMF is induced in the coil, and also current is induced. That induced EMF is also called back EMF, and it is produced in the same coil in which the current is flowing. That's why this process is called self-induction, right? The process of the phenomenon of production of induced EMF in a coil itself. You can write in a coil itself when a changing current is passing through it, and this phenomenon is called self-induction, and induced EMF is called back EMF, right? What is the direction of that induced current or induced EMF? If changing current is increasing, if I increases, then change in magnetic flux also increases. The direction of induced current is such that it opposes this change in increasing magnetic flux. It tries to decreases the magnetic flux, and this is possible only if direction of current is reverse. So direction of current is opposite. Induced current direction opposite to that of the supplied current, right? Induced current always opposes the increasing current, right? But what happens if current is decreasing? If current is decreasing means change in magnetic flux also decreases. So direction of induced current such that it increases the change in magnetic flux. And it possible only if induced current is in the same direction as that of the applied current, right? So you must remember this point about direction of induced current. Induced current opposes growing current. In case of growing current, direction of induced current is always opposite to this direction, right? And in supports dying current, direction of induced current is in the same direction as that of the applied current, right? So you have understood, I think, that what is self-induction. Now next is coefficient of self-induction, or you can say self-induction, inductance. This topic is very important, may generally ask in 1 marks question. What do you mean by self-inductance? What happens when suppose a constant current flows through this coil, and let us suppose I current flows, then due to the current flows through this coil, magnetic flux linked with each coil right now, due to production of magnetic field, let magnetic flux of each coil is phi. Now, let us suppose that there are n number of total turns in this coil, right? N is total number of turns and phi is flux linked with each coil. So, if total number of turns in n, then total magnetic flux phi t is what? N phi. In one coil, phi flux. In n number of coils, total magnetic flux linked with all the coils is n phi, right? And as the amount of the current increases, the magnetic flux linked with the coil also increases. It means magnetic flux is proportional to I. And you remove this proportionality constant and this phi t equal to Li, where L is called self-inductance or coefficient of self-induction. From this one, L becomes phi t by I, total magnetic flux by current, right? You put the value of total magnetic flux, this is n phi for n number of turns, so L becomes n phi by I. This is formula for coefficient of self-induction or self-inductance. What is its SI unit? Its SI unit is Henry, denoted by capital H, and 1 Henry is equal to, what is SI unit of magnetic flux? Weber. Current, ampere. So 1 Henry equal to 1 Weber by 1 ampere, right? From here you can also define self-inductance by taking, if I is 1 ampere, suppose from here after this one, if current is 1 ampere, right, 1 ampere, then L equal to phi t. So you can say that coefficient of self-inductance is numerically equal to total magnetic flux linked with the coil if unit current flows through the coil. You can define in this way self-inductance. Yes, if current is 1 ampere, then self-inductance is equal to total magnetic flux, right? So you write coefficient of self-inductance is numerically equal to total magnetic flux linked with the coil if unit current flows through it, right? In this way, define coefficient of self-inductance. Also, you can define coefficient of self-inductance in terms of induced EMF. First, you take a screenshot of this one, fast. Induction in terms of induced EMF. Here, constant current flows through the coil. What happens if current is variable? We already discussed according to Faraday's law. If current is variable, then flux linked with each coil also changes. And according to Faraday's law, due to change in magnetic flux, what happens? EMF is induced in the coil. And this E is equal to minus d phi by dt. What is this phi t? Phi t here we discussed equal to Li, right? So you write down phi t in place of phi t, Li. Phi t is total magnetic flux because number of total coils is n. Flux linked with each coil is phi, so total magnetic flux is n phi, that is phi t. So you put the value of phi t, Li. L is constant. This L is called coefficient of self-inductance. minus L di by dt. In terms of magnitude, E equal to L di by dt. Negative sign shows direction of induced EMF or induced current according to Lenz's law. So from here, L becomes E by di by dt. Coefficient of self-inductance is equal to induced EMF by rate of change of current. Now from here also you can define coefficient of self-induction in terms of induced EMF. What happens if di by dt equal to 1 ampere second, then L equal to E. So you can define in this way that if coefficient of self-induction is numerically equal to induced EMF linked in the coil if unit rate of change of current flows through the coil, right? Rate of change of current is 1 ampere per second. So self-inductance is numerically equal to induced EMF if unit rate of change of current flows through the coil, right? And in terms of I, you write if I is 1 ampere, L equal to phi t. In this way also you can define phi t. Coefficient of self-inductance is numerically equal to total magnetic flux linked with the coil if unit current flows through it. In both ways you can define coefficient of self-inductance, right? So this is about self-inductance. Next, after this, please take a screenshot of this one. Then we will discuss now self-inductance of a long solenoid. You know, a magnetic field inside the solenoid is what? Constant, and it is given by mu naught Ni, where N is number of turns per unit length. Here suppose there is a long solenoid of length L, right? And N is total number of turns in the solenoid. R is radius of each turn. Right, each turn radius is of R. So and A is area of cross section of the solenoid, right? So A equal to pi R square. Now you have to find self inductance of this long solenoid. So you know magnetic field inside solenoid is constant and is given by mu B equal to mu naught Ni, where N is what? Number of turns per unit length. Total number of turns is N and length is L. So this N becomes N by L. From here you write N equal to small n into L. Capital N is total number of turns and small n is number of turns per unit length. In unit length N, small n number of turns, then in total turns is N, then in that case total number of turns is N into L, right? Now magnetic flux linked with each coil. Suppose each coil magnetic flux is phi and there are n number of turns. So total magnetic flux is what? N into phi. Now phi is what? BA and B is mu naught NIA. Right now? So from here you write total magnetic flux is N into phi. N is what? N into L. Right from here, and phi is what? Mu naught NIA. It becomes mu naught N square IAL. Again you know that phi t is equal to Li, where L is coefficient of self-induction or self-inductance. Then this L becomes phi t by I. You put the value of phi t here for long solenoid, mu naught N square IAL by I cancel, it becomes mu naught N square A into L. This is the expression for self-inductance of a long solenoid in terms of N, where N is number of turns per unit length. In terms of capital N, you write in place of N what? N by L. So this becomes N square by L square, 1 L is cancelled, it becomes L equal to mu naught N square A by L. This is coefficient of self-induction in terms of total number of turns, and this is in terms of number of turns per unit length. In this way you find coefficient of self-induction for a long solenoid. It becomes very easy. If you know total magnetic field inside the solenoid is this one, and using this formula phi t equal to Li, you could easily find coefficient of self-induction. From here it's clear that this coefficient of self-induction depends on what? Shape and size of the solenoid. A and L na? Mu naught is constant, number of turns is also constant. So this coefficient of self-induction or self-inductance depends on area and length. It means shape and size of solenoid. It is not independent on phi and I. On magnetic flux and current, it is not dependent, right? It depends only on shape and size of the solenoid. So I think it's clear to all of you. Please take a screenshot of this one. Then we will move to the last topic of this chapter, that is mutual induction. Now, mutual induction. You already know about self-induction, the phenomenon of production of induced EMF in the same coil in which the current is flowing. Here, mutual induction means there are two coils. One is primary and the other one is secondary. And the phenomenon of production of induced EMF in one coil due to a change in current in another neighboring coil, right? This is called mutual induction. So you can define this way: the phenomenon of production of induced EMF in one coil due to change of current in the neighboring coil, right? How this happens? Suppose this is one coil, primary coil number 1, and this one is second coil, secondary coil number 2. And suppose current is I1 amount of current is flowing in this coil. Due to this current, if what happens? Magnetic flux linked with the each coil of this first one. Na? If current is variable, then magnetic flux linked with the first coil changes, and also this magnetic field lines passes through the second coil or neighboring coil, you can say, right? So, due to the change of current in the primary coil, magnetic flux phi1 linked with the first coil also changes, and hence magnetic flux linked with the second coil, which is kept near the first coil, also changes. And due to change in magnetic flux in the second coil or neighboring coil, an EMF is induced in this second coil. So here current is sending in first coil and EMF is induced in the second coil. This process is called mutual induction, right? So the phenomenon of production of induced current in the neighboring coil if current is flowing in first coil, right? And direction of induced current is again given by Lenz's law of Fleming's right hand rule. I is induced in this direction if current is increasing. Now, next is coefficient of mutual induction or mutual inductance, like self-inductance. How you define mutual inductance? So you know at any instant of time, suppose constant current flows through the primary coil, and this is directly proportional to total change of magnetic flux linked with the second coil. Greater the amount of current, greater is the magnetic flux linked with the second coil. So you can write phi 2 is magnetic flux linked with the second coil. T means total magnetic flux linked with the second coil. It is directly proportional to current in the first coil I1. So this is equal to MI1, or this M is called mutual inductance or coefficient of mutual induction, right? So this M becomes phi 2 total by I1, right? Phi 2 means total magnetic flux linked with the second coil when current in the first coil is I1, right? This is called coefficient of mutual induction. So you can define this way: if I1 is 1 ampere, suppose, then M equal to phi 2T. It means if coefficient of mutual induction is numerically equal to total magnetic flux linked with that coil if unit current flows through the first coil, right? Now, and sign it also Henry. Again, in terms of induced EMF, how you define mutual inductance? According to Faraday's law, EMF induced in the second coil is what? Minus d phi by dt, and phi is what? Phi 2 total is MI1. So you write E2 equal to minus d by dt MI1. M is constant, you take outside. So E2 equal to minus M di1 by dt. Or in terms of magnitude, you write E2 equal to M di1 by dt. Or M equal to E2 by di1 by dt. From here, you can define coefficient of mutual inductance in terms of induced EMF as if di1 by dt, rate of change of current in the first coil is 1. di1 by dt is 1 ampere per second. In that case, M is equal to E2. It means mutual inductance is numerically equal to EMF induced in the second coil if rate of change of current in the first coil is 1 ampere per second. So in both ways you can define mutual inductance or in terms of flux also in the second coil, or in terms of induced EMF also in the second coil. In both ways you can define mutual inductance, and this SI unit is again Henry, right? So in this way, this is about mutual induction and coefficient of mutual inductance. One last topic is left, that is mutual inductance of two long solenoids according to new syllabus. So please take a screenshot of this one. Next, last topic of this chapter is mutual inductance of two long coaxial solenoids, and this topic is also important, right? Mutual inductance of two long coaxial solenoids. Coaxial solenoids means if there are two solenoids and both solenoids have same center, same axis, then you can say that both solenoids are coaxial solenoids, right? Suppose there is one outer solenoid S1, this one is outer solenoid, right? And there is again another inner solenoid, and both solenoid have same axis. This one is the common axis of both solenoid, outer solenoid S1, inner solenoid S2, right? And also suppose that L be the length of each solenoid. Both solenoids have same length, so L is the length of both solenoids, right? Now, suppose I1 current passes through the outer solenoid. Now, what happens when current passes through the solenoid? Now, inside the solenoid along the axis, magnetic field is set up, and that magnetic field, you know, already we discussed in chapter 4, magnetic field inside the solenoid, right? So you just write magnetic field inside the solenoid, and if this current is changing, then that value of magnetic field or also magnetic flux linked with the outer solenoid also changes, right? And if magnetic flux linked with the outer solenoid changes, then inner solenoid is at the same axis as that of the outer solenoid. So magnetic flux linked with the inner solenoid also changes, and there is induced EMF or induced current in the inner solenoids. So if current is passing through outer solenoid, induced current is developed in the inner solenoid. So you have to calculate mutual inductance of that inner solenoid, right? For this, let L be the length of each solenoid. For outer solenoids, R1 be the radius of outer solenoid. This one is outer solenoid, right? And this, from this here, R1 is the radius of outer solenoid. N1 be the total number of turns in the outer solenoid, and small n be the number of turns per unit length. For length L, total number of turns is how much? N1 into L. So N1 is number of turns per unit length. It means N1 by L. So that N1 becomes N1 into L, right? In the same way, inner solenoid S2 has R2 radius, N2 number of turns, and small n2 number of turns per unit length. So N2 is N2, capital N2 by L, and this N2 equal to small n2 into L. Now, suppose I1 current passes through the outer solenoid. Now, due to this current, magnetic field inside the outer solenoid is what? B1. B1 equal to mu naught N1 I1. In the outer solenoid, N1 be the number of turns per unit length. Mu naught is permittivity, permeability constant right now, and this I1 is current passing through the outer solenoid. Now, this is the magnetic field inside the outer solenoid, but both have same axis, same center. So, this magnetic field is also magnetic field inside the inner solenoid also. And if this current is variable, then magnetic flux linked with the each inner coil also changes, right now. So magnetic flux linked with each coil of S2. S2 means inner coil is what? B1. Magnetic field is due to B1 only, right now. So B1 into A. A is actually common cross-sectional area, not A1, A2, because the point where magnetic field lines passes have same cross-sectional area for both outer and inner. So I have taken common cross-sectional area. So this phi 2 is B1A. You put the value of B1 from this equation 1, mu naught N1 I1. So this phi 2 becomes mu naught N1 I1 into A, equation number 2. This is the magnetic flux linked with each coil, means one coil of the inner solenoid. Now there are how many number of total coils? N2 number of total turns. So total magnetic flux linked with inner solenoid is what? N2 into phi 2, right? And N2 is what? N2 into L. Okay, so you put N2 is small n2 into L, and phi 2 is mu naught N1 I1 A. Now this becomes mu naught N1 N2 I1 L into A. Also, you know that total magnetic flux is proportional to how much current is passing in the primary coil, right now. So it is equal to MI1. From here, M equal to phi 2 total flux by I1. So you just divide this total flux, means mu naught N1 N2 I1 L into A by I1. I1 cancel. Then this M, coefficient of mutual induction or mutual inductance, becomes mu naught N1 N2 L into A, right? So from here it is clear that it depends on mutual inductance, it depends on number of turns per unit length and area of cross section, common area of cross section of both the solenoids. In terms of capital N, you can write N1 is what? Capital N1 by L. N2 is what? Capital N2 by L. So you can write M equal to mu naught N1 by L, N2 by L. It means here L square. So one L cancel, A, and here L. It becomes this one. Mu naught N1 N2 A by L. This is mutual inductance of two long coaxial solenoids in terms of capital N, number of turns in both the coils, solenoids. Mu naught N1 N2 A by L. From here it clear that it depends on what? This mutual inductance depends on number of turns, depends on number of turns of each solenoid, right? Now also common area of cross section of both solenoids, right? And length of the solenoid. On these factors, this mutual inductance depends. So this is about mutual inductance of two long coaxial solenoids. It's very simple. It doesn't matter which one is outer, which one is inner. If you find that if current is passing through the inner solenoid and you find mutual inductance for the outer solenoid, then also it becomes same, mu naught N1 N2 L A or mu naught N1 N2 A by L. Both number of turns, it depends on number of turns in both the solenoids, a common area of cross section and length of the solenoid. So both, whatever is the primary coil and which one is the secondary coil, doesn't matter. If current is passing in any one solenoid, then mutual inductance in the other solenoid is same always, right? So please take a screenshot of this one fast. So I think this is the last topic of this chapter, electromagnetic induction. Right now, AC generator according to new syllabus, it is in chapter 7, that is alternating current. So I will discuss AC generator in that chapter. Okay students. So if you want this type of one-shot revision for other chapters also, please write in the comment box so that I will make one-shot revision for other chapters. Okay students, please like, share and subscribe my channel. So please keep revising and stay tuned with this channel. Thank you.